Hello, everybody. Let me introduce our novel model recently accepted by MIDL, and it is called the Cycle-Consistent Embedded Generative Adversarial Network. So our model addresses the problem of generating 3D MRI images from random noise. There have been a number of ways to tackle this problem. A notable one is 3D GAN. So a GAN model consists of two neural networks, a generator and a discriminator. The discriminator will evaluate the output from the generator and therefore produces a score, and it is rewarded for telling the fake MRIs from the real ones. The generator's loss is often the negative of the discriminator's loss. This training process is often highly unstable, and it has a serious problem called mode collapse, whereby the loss function is stuck in a local minima, and the generator keeps generating similar images of one mode, while the discriminator essentially gives the same score to the generator's output. The first row as our desired training progress, and the second row is one with mode collapse. So an alternative to the GAN is called variation auto-encoding GAN. This model adopts the structure of VAE, having an encoder and a decoder, which is also the generator in our case. This model not only learns the mapping from the prior to the posterior, but it also learns the mapping from the real MRIs to the latent space. And it does that by having the encoder learn two parameters, the mean and the variance of the random prior. The structure is known for solving the mode collapse in GAN because it builds on the principle that having a nice convergence in the latent space will help prevent the generator from entering a mode collapse. That comes with a side effect, unfortunately. The encoder aims to learn only two parameters, the mean and the variance, so the output is essentially Gaussian. This process will lose too much information from the original distribution. So now we can see the comparison of the real images and the VAE GAN's output. So this is a direct result from using KL loss and two-parameter output in the latent space. So the next solution is called 3D alpha W GAN. It adopts the structure of alpha GAN, and it also uses the Wasserstein gradient penalty. So this model also tries to learn some nice conversions in the latent space. So it uses a co-discriminator, which is neural networks consist of mostly linear layers. And this model will distinguish the encoder's output from the real Gaussian. Based on our results, this model solves the mode collapse, but its latent space convergence is not as good as it promises. Shown in the first image, we can say that the learning of the latent space has essentially diverged because the blue curve is the loss curve of the co-discriminator, and it diverges out of range from the loss curves of the discriminator and the generator. We also samples from the output of the encoder, and it turns out that encoder's outputs are in a completely different scale from the real Gaussian noises. So we decide to fix the latent space divergence of this model by replacing the co-discriminator with a much more simplistic Wasserstein loss. So we calculate the Wasserstein distance between the samples from the standard Gaussian and the output of the encoder, feed those outputs back to the encoder, and produce two reconstructed vectors, ZE and ZRE. And this is when we derive the cycle-consistent loss from these two vectors to the standard Gaussian vectors. And then we add those two terms to our loss function. We qualitatively evaluate their encoder by using principal component analysis. We sample from the output of their encoder and plot the distribution in two-dimensional form. The most sparse distribution is from the 3D alpha W GAN. That is also the model with the highest divergence. WAE GAN has the distribution surrounding the real Gaussian vectors. Our eventual model and the VAE GAN have the best coverage. Now let's take a look at the PCA analysis of the image space. We can see the light blue dots, which are the outputs from the 3D alpha W GAN, are spread out similarly to the real image distribution, which means that this model solves mode collapse. And if we take a look at the distribution of our models, CCE-GAN and WAE GAN, and they're also pretty similar to the real image distribution. However, VAE GAN's distribution are clustered in the center. This is because that the blurriness of VAE GAN's output is so serious that it essentially makes the image very similar to each other and essentially results in a mode collapse, which is unexpected from VAE GAN. Let us take a look at the quantitative results. First of all, for the latent space or Z space, we use the maximum mean discrepancy, the MMD metric, to measure the distance between the output distribution and the Gaussian distribution. We sample from the encoder's output and also from the Gaussian distribution, and then we use the MMD to measure the distance between them. And it turns out the models that have the shortest distance are VAE GAN and our model. And for the X space or the image space, we also do the same thing to the generator's distribution and the real image the training set. It turns out that the VA-GAN blurriness actually reduces the distance if we use linear kernel for MMD. And that's why the linear MMD produces inaccurate result for VA-GAN. And the second best is our final model. That's why we used another kernel, RBF, and it generates a nice result for our model. We also used another metric called structural similarity. The closer that the SSIM score is to the structural similarity of the real distribution, the better it is for the model. And the model's SSIM, in this case, is 0.839. The best model here is 3D alpha GAN. To be conclusive, we built our model on top of 3D alpha W GAN, and we essentially solved the divergence in the latent space. We believe having a desired prior can lead to alleviation of mode collapse and also the blurriness in the images, therefore creating generation with better quantitative and qualitative results. Thank you.